Right, I want to talk to you guys in this video a little bit about the concept of electronegativity and what that means for something called bond polarity. Well, we'll talk about what polarity means here in just a minute, but for right now we're going to focus on the word electronegativity. And in simple terms, electronegativity is really just a measure of how strongly does an element want to hold onto its electrons. All right. This chart gives you an idea about the relative electronegativity values of elements across the periodic table. All right. The noble gases are not included here because they're essentially not electronegative at all, particularly the top ones. But when you look at this table, what do you see in terms of a trend of electronegativity? Well, you can see the numbers go up from left to right and from bottom to top, with the most electronegative element in the whole table being fluorine. In fact, across the table you can see that the halogens are the most electronegative elements in each of their groups. These are the most electronegative elements. And on the other hand, the least electronegative elements appear to be the group 1 metals. Now that's got to be something to do with their electron configurations, and it actually does. Fluorine and all these guys, we've seen before that these guys have 7 valence electrons. So for example, fluorine has 7 electrons. It wants one more. And because it only wants one more, it really wants to hold on to these. Alright? And the trend decreases down here simply because the atoms get bigger. There's a weaker hold onto the electrons. But the point is, out of all the elements across each period, these guys have the highest electronegativity, fluorine being the highest of the bunch. So these guys have the highest electronegativity, and over here these guys all have, they're all in group 1, they all have one outer electron, and they have no desire at all to keep that. They just want to get rid of it. That's why their electronegativities are so small. Now the reason why electronegativity is important is because it has an effect on something called bond polarity. That's to do with how the electrons are shared in a bond. All right? If we have two elements, A and B, whatever those may be, you can have a situation where the electrons are held right in the middle, equally between the two elements, or, for example, where the electrons are held more strongly by one element than the other. So, for example, like this, where the electrons are not held equally in the middle of the bond, because one's more electronegative than the other. If we had, say, fluorine bonding with, for example, hydrogen, you can see fluorine is much more electronegative than hydrogen is, so therefore it would hold onto the electrons in this bond much more strongly. So the electrons will be displaced much more towards fluorine than hydrogen. All right? And because electrons have a negative charge, in this bond there'd be kind of a net negative charge on the side of the fluorine because of where the electrons are. And if there's a net negative charge here, there's a net positive charge on the hydrogen. And the reason why this is important is because this charge separation has an effect on the reactivity of this molecule that this one doesn't have if the electrons are shared right in the middle. So, bond polarity really comes down to where are the electrons in the bond. Are they shared in the middle, right in the middle, or not? All right. Now, if this electronegativity difference gets big enough, what happens is the electronegative guy pulls the electrons towards itself so much. The analogy here is imagine that you have a rubber band, or what you guys call an elastic band, or whatever you guys call it, and you pull it and pull it and pull it. Imagine that what's happening is that means your bond's getting longer and longer and longer. The electrons are getting more and more displaced from the center of that bond. What's going to happen if you pull that enough? Well, it's going to snap, of course, and it'll probably hurt your fingers. But the analogy there is if you stretch this enough, if you make that electronegativity difference big enough, the bond will break, and you'll actually end up with a transfer of electrons and an ionic bond. All right? So, how do you figure out what sort of bonds you have, given a couple of elements? Well, I'll show you. All you need is access to a table like this. This is not the table from your book, but the numbers are pretty much the same. What if we had, well, let's just take a look at this first. This is a table that shows you the different types of bonds, the 3 different types of bonds that we could potentially have. There's only 3 possibilities we can have. You can have a situation where your electrons are shared equally between the 2 atoms, all right? And the way you figure that out is by the electronegativity difference, the delta E here. If there's a small difference in electronegativities of the two elements, they'll be virtually, the electrons will be shared virtually in the middle. The bigger that difference, the more towards one element the electrons are removed. And if the difference is so big that there's no sharing at all but they're actually transferred, then you get ions. Alright. So to give you guys an example, hydrogen, or indeed two elements of exactly the same atom, or two atoms of the same element. Because these two have exactly the same electronegativity, because it's two atoms of hydrogen, the difference here is 2.1 minus 2.1, which of course is 0, meaning those electrons are shared literally right in the middle of that bond. There's no charge separation whatsoever. When we come to something like HCl, the difference here is, well, chlorine's 3.0, hydrogen is 2.1, the difference there is 0.9, and 0.9 fits between this 0.4 and 1.7 range. Therefore, they call this polar covalent bond, because the electronegativity difference is higher than 0.4 or less than 0.7. That means the electrons are displaced towards the more electronegative element, which of course is chlorine. So it looks something like that. Because of that, there is a charge separation here that there is not here, because the electrons are right in the middle. Now when we get to something like this, sodium and chlorine, alright, we already know the electronegativity of chlorine is 3.0. The electronegativity of sodium is 0.9. Now 3.0 minus 0.9 is 2.1. 2.1 is higher than this 1.8 cutoff, so therefore that means that electronegativity difference is so high that the chlorine actually breaks the bond and pulls the electrons towards itself, so there's no electrons being shared at all. So that means that the chlorine has grabbed the electron from sodium. Chlorine's gained one, sodium's lost one, that's where the charges come from, and what we have are ions, right? Okay, so what if we had a bunch of sets of elements? Can we figure out if the bonds between them would be non-polar covalent, polar covalent, or ionic? Well, of course we can. It's a really very simple issue. All we need is a periodic table with electronegativity values on it. And of course I would give you something like that on a quiz or an exam, because I get the feeling if I asked everybody, do you want to memorize this table? I have a feeling everybody would say no. And I wouldn't be surprised, because that would suck. Alright, strontium and sulfur. So really the only things we need to know here are, what do we have? Well, strontium has an electronegativity of 1.0. Sulfur has electronegativity of 2.5. So therefore what we're looking at is we take the biggest one, subtract it from the smallest one, and what we get is an electronegativity difference of 1.5. And of course that puts us in a polar covalent bond, because that's more than 0.4 or less than 1.7, with the electrons being displaced towards the sulfur, giving us a bond that can be represented by this. Alright. Now one key thing here is whenever you have a metal, the metal is always going to be the least electronegative element, so it's where the electrons are displaced from. The non-metal is always going to be where the electrons are displaced towards. Now here we have potassium and fluorine. First of all, we have potassium, which we know has a very low electronegativity. It's a group 1 metal, and fluorine, which has the highest electronegativity. That's probably going to tell us it's going to be ionic. Fluorine is 4.0. Potassium is 0.8. Oh, we did this one already. Bollocks. Okay, all right. So therefore, that means that difference is 4.0 minus 0.9, which is way higher than the 1.8 cutoff, meaning there's no actual bond here. Fluorine's grabbed that electron from potassium and given us an ionic attraction there. Okay, there's still a bond there. It's just a attraction between two charges. There's no sharing of electrons anymore. Iodine. Now the thing to be careful about here is iodine has an electronegativity of 2.5. However, in this case it doesn't really matter, because you've got the same thing bonded to itself. So of course 2.5 minus 2.5 is 0, that means that bond is going to be non-polar covalent, where the electrons are shared exactly equally between the two iodines, and there's no charge separation there at all. Now, phosphorus and bromine. Phosphorus is electronegativity of 2.1, bromine's 2.8, giving us a difference of 0.7, which is in a similar situation to strontium and sulfur in that that fits in the polar covalent category. All right. However, this is kind of a sliding scale. This bond is more polar than this one because the number's bigger, but they're both still classified as polar covalent, where the electrons are displaced towards bromine, and there's still that separation of charge there. The delta sign here is just a lowercase Greek symbol delta, just meaning small amount. And for carbon and hydrogen here, carbon electronegativity is 2.5, hydrogen's 2.1, giving us a difference of 0.4. Now, technically, according to our table, that puts it right at the boundary of non-polar and polar covalent, which means it is classified as polar covalent, but only very slightly. All right. But the key here is, can you recognize or can you figure out if a bond is polar, covalent, non-polar covalent, or ionic? And this is how you do it. An understanding of this is useful for when we come to combining bonds into molecules and figuring out if entire molecules are polar or not. But anyway, that's how you figure out polarity of bonds using electronegativity.